This is my derivation of what's called the free spectral range, and a fabry perot cavity or laser. So if this is your gain axis and this is your frequency axis, you should get a curve whose envelope is whatever, and the frequencies exist as discrete lines with spacing between them, and the spacing is called the free spectral range, the FSR. So here's my derivation for two cases: one when there's dispersion, two when there's no dispersion. So we'll obviously start with no dispersion. So there are two stability criterions. One has to deal with the gain, the other has to deal with the allowed frequencies in the cavity, in the resonator. This has to do with the second one. So second condition amounts to having an integer number of half wavelengths equal to the optical length, the length of the resonator times the refractive index of the resonator. If we substitute lambda for the frequency, we can get this expression. And if we want to know what's the FSR, we want to express the next frequency, like the neighboring one. So since this remains a constant, we can just equate it to an expression of the same form, just with m plus 1, and the frequency increased by that very same FSR that we're looking for. So the idea is to develop an expression for that, to understand what this is. So now we have an equation of sorts with some straightforward algebra. We get to this equation. We can substitute for this the ln eta, or ni. It's actually ni, I think. Yeah. Eta is this. So we use this equation to substitute mc over 2, and we get the expression for the free spectral range and the non-dispersion case. So notice that the free spectral range is a constant in this case. It depends only on the refractive index, the length, and the speed of light. If we want to do the same or something similar, but for the case where there is dispersion, we start with a similar expression where I've already shifted, where I've already switched from lambda to ni. The neighboring frequency is written in the same form, but m becomes m plus 1. Ni has its has that additional term that we're looking for, and of course, as we said, the refractive index does not remain constant and is increased by what you can treat as a linear approximation of the refractive index, where n prime is the derivative of the refractive index with respect to the frequency, and delta ni is the same delta ni here, the frequency, the FSR that we're looking for. So again, with some straightforward algebra and usage of the original expression, we can get to this, where we see that we get almost the same expression, but with some important differences. So before, in the non-dispersion case, we got delta n, C over 2ln. Now, this n has an additional term, which is n prime times n plus del n. This is this should have a multiplication sign here. God damn it. Whatever. This is not the same as this. Here I say that n plus n prime delta n. This is just n at n plus del n. So there's no multiplication sign here, and there is here. We can further rearrange and say that n plus n prime times del n is that very same one from above. This is the refractive index at the neighboring frequency, and here is the additional term, the n prime n. So what's so basically, if n doesn't change, doesn't depend too strongly on the frequency, we can treat this n, we can sort of like approximate and say that this n is almost as just saying n of n. This delta del n doesn't change it much. What does matter here is this additional term. So we can just rewrite this more neatly as del n, the FSR in the dispersion case is just the speed of light over 2 times the length times not just the refractive index, but the refractive index plus the change. That's the delicate point. This is not the change in the refractive index. If it were the change in the refractive index, it would say n plus n prime del n, but it's not. It depends on the frequency, not the change in frequency. And that is a very big difference. So, because usually the change in frequency might be very small, but the frequency, as we're dealing in optical frequencies, could be very, very high. So, yeah, so that's it. Did I have anything else? Oh, yeah, and the last point is that you could actually, we recognize this, C over n plus n prime n, as the group velocity. So basically we can just say that in the dispersion case, in the non-dispersion case, we got that the FSR is just C over 2ln, but in the dispersion case, it's actually the group velocity over twice the length. So now I'm done.